So assuming that we have a surface that we can think about, what do we do with that surface? Well, one could calculate the slope of it. We'll see why that's useful as we continue, but for now let's just generalize our idea mathematically of what a derivative is to functions of several variables. This leads to the concept of what's called a partial derivative. For functions of one variable, the idea of a derivative only has one meaning. You can move along the function and the slope of the function changes. For functions of several variables, you can move around the function in different ways. You could follow the x direction or the y direction, for example, if one's looking at a function in 2 dimensions, or one could go in any different direction you like. In the next course in mathematics, you'll look at how to go in any direction. For now, though, we'll concentrate on moving along the coordinate directions in the x and y directions, which give us the partial derivatives. So if we have a top-down view of a function, which we might think of as some level surfaces like this, we can then take derivatives in the x direction, move in this direction, or in the y direction, and these give us our partial derivatives in the x and y directions. So in the x direction then, we just define the derivative as though y doesn't exist, it just is a constant. So we fix a value of y, and then take a derivative in that direction. So imagine we fix a direction, fix a value of y, and then calculate, slice through the function, and evaluate the derivative along that path. That means we can think of the derivative in the usual way as the limit as h tends to 0 of f of x plus h and y minus f of x and y. So we don't change y in the procedure. We take this limit, and this gives us the partial derivative, which we write as df by dx, but we use a funny curly d instead of a straight d to remind us that we're taking partial derivatives and not normal derivatives. So this we would say is the partial derivative of f with respect to x, and we treat y as a constant. It's also written as f subscript x, or if we write z equals f of x and y, this would be dz by dx. And sometimes one would explicitly say that y is a constant, and that's written with a vertical line. Similarly, in the y direction, we move along a line where x is equal to a constant and form the partial derivative with respect to y. So in this case, we vary y. We look at f of x and y plus h minus f of x and y over h and take the limit as h tends to 0. And so because the definition is the same as we do for single variable calculus, all we do really is a conceptual change. So if we take an example, now if I calculate the derivative with respect to x, then both terms in this expression involve x. So the first one I differentiate to give me cos x, and the second one I treat y squared as a constant, so it would be exactly the same as if it was just the number 2, so that gives me y squared, just the constant part. The derivative with respect to y. Now the first term, sin x, does not involve y, so that's just like differentiating a constant when I differentiate it with respect to y, so this gives me 0, and the second term I differentiate with respect to y, giving me 2xy. So these now give me independent functions of x and y, and you can think of those as new functions of two variables. We can also form second derivatives and higher derivatives in the same way as we do for single variable calculus. We just differentiate the function again. So given first derivatives, fx and fy of the function f of x and y, I can form a bunch of new partial derivatives. I can take the derivative of the x1 in the x direction, giving me the second derivative with respect to x, d by dx as an operator. So these are just different ways to write out the second derivative with respect to x. We then have the mixed partial derivatives, the derivative with respect to y, followed by the derivative with respect to x, and fxy, which is the derivative with respect to x, followed by the derivative with respect to y. So note the ordering in the two notations. So take the function as an example, f of xy equals log x over cos y. The first derivatives are fx equals 1 over x cos y, where I just differentiate the log, and fy is minus log x over cos squared y times sin y, where I differentiate the 1 over cos. So then I form the second derivatives with respect to x and then with respect to y. And now I form the two mixed derivatives. If I differentiate fx with respect to y, I get minus sin y over x cos y. And if I differentiate fy with respect to x, this becomes, and what you'll notice is that these two things are the same. And that's not a coincidence. Provided the derivatives exist, always have. So we say that partial derivatives commute. It doesn't matter which order you take them in. And this also applies to higher derivatives. So if I have the derivative of f with respect to x, then y, that's the same as the derivative with respect to x, then y, then x, which is the same as the derivative with respect to y, and then x, followed by x. What's the interpretation of these partial derivatives? If we have some surface, and we choose a point on that surface, and a tangent line in the x direction, tangent line in the y direction, have slopes fx and fy.